So thank you very much to be with us in one more of the Sci-Cafe colloquial talks that are organized by the International Relations Office of the Hellenic Mediterranean University in collaboration with our new research facility. Me and George Kavoulakis, we are very glad to have today with us Professor Nektarios Papadogiannis. For me, Nektarios is like a hero when I was an undergraduate student, not because of his football capabilities, but because as a physicist. So I totally believe that the whole generation of physicists from the generation 1991 to 1996, we admire Nektarios for his knowledge and how friendly he was to all the undergraduate students. So Nektarios has a bachelor degree in physics and a PhD in physics again from the University of Crete. He's one of the top scientists that we have, and I believe one of the top scientists in Europe regarding laser pulses and their application. Actually, he was in the core team in Institute of Electronic Structures and Lasers that they have measured experimentally attosecond laser pulses. And now he's involved in the administration of the university, but also he's an active researcher in the Institute of Plasma Physics and Lasers, one of our research facilities within the Hellenic Mediterranean University. So Nektarios, thank you very much for your contribution. It's very important for us as an international relations office and as a research institute of the Hellenic Mediterranean Research Institute that we have the honor to have with us also Manolis Kimakis, who is the director, to be with us. So the floor is yours, Nektarios, and thank you very much.
Thank you very much, Kostas, for your kind introduction. And also, I really remember old times in the physics department when we are both students there. I enjoy your attitude, not only in basketball, but also in physics and in applied physics. I would like also to thank Giorgos Kavoulakis, also a very good friend of me for these ages for the organization. I'm very glad to be among colleagues, friends, and people that they are interested in this kind of applied physics, like the laser matter interaction and the secondary sources like novel X-ray sources with high coherence. And I'm also very glad that the rector of our institute and also the vice president of university research centers is with us. And some also people from abroad that they are interesting. Some of them I know very well. So let's start my talk, novel X-ray sources with high coherence. And I will give the prospects of this kind of things, the new horizon in biomedical imaging, which is something quite important in the field of application. So some introduction, first of all. Let me hide this. Okay, let's discuss a few things about coherent versus chaotic or thermal light. So when we have some thermal light sources like the old bubbles of wolframium lamps, the emission of the light is completely incoherent. The incoherence means that the phase front of this light cannot be defined very well. So the waves that propagate far from the point of the radiation is completely chaotic. So we cannot add them coherently. This is the so-called, for example, black body radiation that we know that depending on the temperature of the emitted matter, there is different colors, and the visible is around 6,000 Kelvin, like our sun. Now, we can put some coherence on that if we add a pinhole aperture, so we produce a point source, and according to Huygens principle, we can have all the colors, but then by putting a filter, we can have a monochromatic wave with very good phase front. This is a partial coherence that we can do with spatial localization of light. the emission of this kind of light, if you see the quantum nature of incoherent light, is the so-called spontaneous emission. So spontaneously, an electron that is excited in an excited state throw down to a level with less energy and emits a photon. This is something that we cannot really understand very well. Only a very sophisticated physics theory like the quantum theory, electroquantum theory of light, quantum electrodynamics, explain that is something that connected with the so-called vacuum fluctuation. So this is something that is completely statistic. So we cannot really have photons that emitted at the same time, so it's impossible to have a phase-front coherence. Now, in our days, we have very good coherent light sources in the visible area with the so-called laser light amplification by stimulate emission of radiation, where we use another quantum technique, is the stimulate emission, where initial photons that originate for spontaneous emission can make the electric field of them make the electron to fall in an energy state with lower energy, and the emission of photon, which is exactly the same than the initial photon, same direction, same wavelength, same coherence. So finally, we have photons that, like soldiers, follow the same road with the same, more or less, frequency. So this is coherent light, and by this way, we can have really very, very well good phase fronts. Now, in order to distinguish between the thermal lights and the coherent light, it's experimentally, we have to do the so-called quantum statistics. We have to reduce the intensity of the light so much and to have a specially designed detector in order to have photons measuring in photon level and do photon counting. So if we plot the probability as a function of the photon number, the probability to have 1, 2, 3, 4 or more photons in every measurement, we will see that in thermal light, there is an exponential decay of this probability, while in coherent light, there is a Poisson-like statistics, and we have a maximum, which is actually the intensity of the light. Here is 10 photons. So this way, we can distinguish between quantum statistics, using the quantum statistics between thermal and coherent light. Now, in previous 30 years, there is a revolution of imaging of matter using these coherent light sources, which is invisible and in IR. So I will say some example very fast. The non-destructive laser vibrometry, where we use the laser do holography, for example, here to see the noise in the external part of the car when the machine of the car works. So with this way, we can reduce the noise that go inside the cabin of the car. We can do laser endoscopy imaging using coherent light. So we have very good icons with endoscopy using optical fiber. We can have laser speckle imaging. Speckle is a coherent part of the light that appears only if we have a coherent light there. We can have laser photoacoustic endoscopy, where we use the light in order to produce acoustical waves, and by this way, the acoustical waves penetrate inside the material, and by echoes, we can do an image, very good image of very, very short structures, especially with ultra short pulses. We can produce mechanical waves in the order of less than micrometer, in the hundreds of nanometers. So we have the ability, because of the coherence of the wavelength of the acoustic light, to observe very small structure inside the matter. And we have also the so-called second harmonic or nonlinear imaging, where we can illuminate with a laser light biosample, for example, and then by observing the second harmonic generation by the matter and imaging the second harmonic, we have a very good ability to go up to few microns in order to observe different kind of material structure using this second harmonic and nonlinear effect. And also we have the so-called ultra-fast laser imaging of chemical reaction. For example, I remind you the Nobel Prize in 1999 in chemistry by Ahmed Ziveil, where someone can use a femtosecond laser to excite, for example, long molecules like biomolecules and observe exactly, this is experimental results, where someone observe exactly the dissociation of very big molecules. And here is the molecule before the excitation, here is the point of excitation, and there is some femtosecond after the excitation of the molecule. So we can actually follow chemical reaction using ultra-fast laser imaging of using laser light. Now, if we want to do imaging, and most of the imaging use the diffraction of the light, using coherent or using thermal light, there is a very big difference. For example, if we have a sample with different diffracting centers, and we use incoherent light, the only thing that we can see in the far field in the diffraction pattern is a cycle that the angle between the center line and the cycle here is nothing else like the wavelength, the central wavelength of the radiation divided by the average distance between these diffracting centers. Now, if we use now a coherent light, there is a completely different picture. We can see this kind of speckles here, and we can really by Fourier transform the icon in XY space, we can really go back and see what is exactly the location of these diffractive centers. For example, if we have this kind of diffractive center and we do a diffraction experiment using incoherent light, we have this kind of icons. Here you see that there is changes of diffractive center location in space, and you see that in incoherent light there is no any change in the far field in the diffraction pattern. While if we have a coherent light in coherent case, you see that by changing the diffractive centers, there is a difference in the diffractive light, and this is very clear in this picture, where we have from around a pattern. Here we have a pattern that is a line pattern, and you see here the difference in the diffractive line. So we are able, if we use coherent light, to observe really detail of image detail of the matter that we want to image. Now, let's go back to fundamental optics and to Abbe theory. Now, coherent light sources approaches the diffraction limit. So this is a so-called Abbe diffraction limit, where if we want to image a certain point here, the resolution delta x equals more or less the wavelength of the light that we use, divided by 2n sinus A. A is the angle here, and n is the index of diffraction of the matter that we want to image. If we use NIR visible UV coherent light, the wavelength is in the order of 0.2 to 10 microns in the IR. So theoretically, with this kind of light, coherent light, of course, every time, we can reach a spatial resolution at few hundreds of nanometers. Practically now, this is the best achievable resolution, but it's very difficult to go beyond 1 micrometer using direct laser light. And there is another problem is that visible light cannot penetrate deep in matter because of absorption. Now, if we go to another area of spectrum, so VUV, XUV, or X-rays, where the wavelength is for 0.1 to 200 nanometers now, there is theoretically a very, very big, a very, very small resolution, which may reach a few nanometers. So Now, the question is there any X-ray facilities that produce, for example, coherent light? Yes, there is the so-called free electron laser, XFL facilities, who provide coherent sources of directional and high brilliance X-ray radiation. As you see later on, they require a very high budget and very big facilities. The maintenance is very expensive, and manpower operation, and for this reason are only few worldwide. So it's there is since the X-ray light penetrate deep in matter, it's obvious, I think, that we need to generate versatile VUV, XUV, X-rays, coherent sources in several laboratories in order to be used in the future for imaging and bioimaging. Now, let's see a bit of the evolution of X-ray biomedical imaging. By Röntgen was the Nobel Prize was the initial experiments where they used the so-called bubble, X-ray bubble, that with thermionic emission, electrons are accelerated by a high voltage in an anode, and then there is a generation of X-rays, fully incoherent X-rays. There is not so many coherence. So using this kind of things, and by aperture the beam, we can do the so-called the X-ray radiography that most of us, we have already been examined by this kind of things. And we have also more sophisticated, the computed tomography, where we have a bit of point sources. There is a turn of this source, and we do different kind of icons, and then by sophisticated algorithms, we can go back and have a 3D image of the material. And nowadays we have the so-called CT CAT scanners and micro CT, where we use it to observe small materials like cells or like other kind of materials that is important in biomedicine. All of these kind of sources, they use incoherent light, and they aperture the light in order to have some coherence. So they have no really the best ability. I mean, the image cannot be really less, the resolution cannot be more than many hundreds of microns. So this is something which is very good for long observation of long matter difference in density, but it's not good in nowadays in the period of nanomaterials, in the period of nanostructure materials, in the period of biology and genetics. So the goal is to build a cost-effective and a reasonably sized X-ray laser that will provide ultra-high resolution imaging, and we know very well, and I will prove you that with ultra-short laser-like beams contains a broad range of X-ray wavelength, coherently summed at once, and we can focus them both in time and space. So we have a very, very good spatiotemporal resolution. And this source of coherent like spans covers a huge region of electromagnetic spectrum, so we can able with to do the so-called multispectral imaging, so to have different light coherent in the X-rays for different material that we want to observe. So the goal practically is to improve the current situation. The X-rays in the hospital now are limited. They cannot detect, as I said before, sub-millimeter cancers, for example, because the X-ray source is like a light bubble than a laser. So the goal is to improve the X-ray imaging resolution at your doctor's practice by thousands of times. And I think I persuade you that the need of this kind of research. So I will go faster. Let's go back to physics. Some X-ray optics here. The material index of diffraction in the X-ray regime is given by this equation. So index of diffraction equals to 1 minus delta, and this is something because of plasma, because of ionization, because the X-ray light is ionized light, plus I vita, where vita is the absorption coefficient. So and this delta, this small delta, comes from the quantum nature of ionization, and R0 here is the classical electron atomic radius, lambda is the wavelength of the X-rays, and E is the electron density of the plasma. So if we write a propagation of a wave here by the electric field, we can finally in the end have something that this is the absorption, the exponential decay, the Maya absorption of the X-rays, and here is a phase different in the phase of the wave because of delta. It's clear by this analysis that Vita causes the X-ray absorption. So if you do X-ray radiography in a hospital now, they use the parameter Vita, and they use the difference between the absorption of bones and of tissues, and by this way they do the imaging. While if you have a coherent light, you can use delta, the phase difference, and this is something very important, as you can see in the next transparencies. So let's go back now to see the high power ultra fast lasers as a tool to generate coherent X-rays. You know very well that in 2018, the half of a Nobel Prize was given to Gerard Mourou and Donna Stickland. This is the period that they performed the research for the Nobel Prize in 1989, 1990 at Rochester University in US. And they received in 2018 the Nobel Prize because of their method to generating high intensity ultra short optical pulses. And this is myself in 1999 in Mourou lab, where we try to do coherent X-ray sources using really gases, and this is the experimental setup that I had in this period. So the basic idea back of ultra short laser pulses is the following. When you have one frequency in the frequency spectrum and you do a Fourier transform, you have all time duration, so you have a continuous source. If you have a delta function in time, then you have the whole spectrum in frequency. This is actually the method bug of preparing very short pulses. We have a material that emit light in a Gaussian-like emission. And then by using a laser cavity, we have here the cavity longitudinal mode structure. If we multiply this thing, finally we have a spectrum which is the cavity longitudinal mode structure. And because the laser is coherent, we can do coherent summation there. And by this way, with the coherent summation, we have the so-called mode locking, where we have here pulses that they are very, very short in time, ultra short pulses that repeat themselves after the coherent constructive addition of these waves as you see here. This is the resonator round trip time, where we have, for example, in an oscillation of a femtosecond laser, something about 100 of megahertz. So this is nothing else like light synthesizer. So we have some different frequencies here. You see the difference in the frequency, where if this is coherent summation, we have coherent light, we can produce a pulse that is very, very thin, very, very fast in time. Imagine that the period of the light in the visible is something about from 2 to 3 femtoseconds. So you see here that the lasting of this pulse can be in the same order of a few femtoseconds. Now, the idea of Mourou and Stickland was nothing else like how to increase the number of photons by this way. It's a so-called chirp pulse amplification, where we have a short light pulse from a laser. We use a pair of grating in order to do a chirp of the pulse. So we have to separate all the colors of this pulse in time. So this is a chirp pulse where the red is first and the blue is back. We do this, the idea of Mourou is to do that in order to reduce the number of photons per time that reach in the amplifier, because if we try to amplify directly this beam, the amplifier will be destroyed, the optical parts of the amplifier will be destroyed. And by this way, we can really increase, amplify the light, and using exactly the opposite technique of the grating pair. Here we can take back all the difference in time of the various color, and finally we have a pulse which is very, very short in time, but at the same time have a lot of more photons, and this is the amplified pulse. This is the CP pulse amplification method that gives Mourou and Stickland the Nobel Prize 2 years ago. So we have such a laser in our institute in IPPL in Hellenic Mediterranean University, which is the peak power of this laser is 10 to 14 watts is, in the region, so it's 50 terawatts. The peak intensity at focus reaches 10 to 20 watts per square centimeter. And if you calculate the AC laser electric field in RMS is something about 10 to 13 volts per meter, a huge electric field. And the electron acceleration, if you use this electric field, can reach 10 to 23 G. So now let's go. I described the tool, and now let's go how we use this tool to produce coherent tabletop XUV sources, the so-called high harmonic generation. I will present a video in order to understand the high harmonic generation physics back of that, preparing the Rochester University this video. So a high harmonic generation, we need a gas, an atomic gas, where emits there the atoms. And we have a 25 femtosecond laser. You see the atoms, the laser interacts with the atomic gas, so drives the gaseous atoms. If we go now in a single atom picture, you see that there is an oscillation of the external electron because of the AC field, electric field. And every time that passes inside the core can recombine and emit this very short burst of radiation, which have very high frequencies. And this is the so-called high harmonic generation and high harmonic generation. We want also to have coherent summation of this light, otherwise can be destroyed. So we have to have the material in certain way that we have coherent summation in order to increase more and more the light of this kind of radiation. Now, if we have a spectrograph, a spectrometer here, and the camera, we can observe here light that is only in certain frequencies in the X-ray area, XUV area of spectrum, where there is a distance between them that is two harmonics. So we have only the odd harmonics because of the symmetry of the atomic gas, where in period we have this kind of generation of light. Let me stop this. Sorry, there is a small problem. Okay, so let's now see here the quantum picture. So imagine that we have a localized electron here. The electric, and here is a 3D picture where this is the time in femtosecond, this is the probability, and this is the distance. So we observe the wave function of an electron, where initially is a classical electron, you see are localized. The electric field of the laser do the oscillation of this electron, and as the oscillating the electric field of the laser, twice per laser cycle pass through the center, and there is a structure here that is very noisy, and this is the so-called quantum interference that produces the harmonics. If we Fourier transform up to here in time, we have a classical power of emission of a classical electron, which is the so-called Larmor theory, Larmor generation. If we Fourier transform up to here, we try to see some structure in front of this emission. And if we Fourier transform in the end of this kind of radiation, we see here the so-called typically harmonic spectrum, where we have only the odd harmonics of the light, fast drop, plateau, and cutoff, And this is a picture in quantum mechanics. Now in experiments, when we use a gas cell or a gas jet, where we focus the femtosecond laser light, and after we use some X-ray optics and X-ray cameras or MCPs there in order to observe this span of harmonic lights that are located in the area of few tenths of a nanometer. Now, if we go in semi-classical model for high harmonic generation, we can describe the whole thing with a classical, semi-classical model. So we can have the electric field of the laser, the Newton's law, and we calculate the velocity and the position of an electron accelerate inside the electric field. So we understand by this is that this is the electric field of the laser. So there is some emission times there of the laser where we have recombination. This is the quantum trajectory of each electron. We can have recombination at this point. We can have recombination at this point, or we can not have recombination. And in this quantum trajectory leads to ionization of the atom, while this quantum trajectory leads to high harmonic generation. But you see that there is a very short path, and the so-called short trajectory, and also this trajectory here, we have recombination in the center, but is longer the path, so we have the so-called long trajectory. Now, the measurement of the spectrum is fast drop, plateau, and cutoff. Since the emission is twice per laser period, this means that if we Fourier transform that, we have 2 omega spacing between the harmonics here. And the important thing here is that if we plot the short and the long trajectory here, the plateau harmonics, they are generated by both short and long trajectory, while in the cutoff region, which is here the maximum energy, reaching something about 3.2 UP plus IP, here the maximum energy having only one intermediate trajectory. So the cutoff harmonics are really have very good coherence. Here the short cutoff, there is a positive chirp, in the long harmonic we have the negative chirp. So by this way, we can say that plateau harmonics are high intensity harmonics, but they have both short and long, and we need some way to separate them. And in cutoff harmonics, we have only one kind of generated way. We have only intermediate, because the difference in phase is very huge between the short and the long harmonics, since the electron spends more time in the continuum when we have the long trajectory, whilst less time in the continuum when we have the short trajectory. So there is a lot of difference in the properties of the emitted light. This is actually what is shown in this kind of graph, where plateau harmonics, low harmonics, they are generated both. You see blue here, purple here, purple here. So both these trajectories generate this kind of light, where as we approach the maximum energy here, we have only intermediate trajectories. So the maximum energy, the cutoff energy, is calculated to be IP, which is the ionization potential of the atom, plus 3.2 UP, where UP is the kinetic energy of the laser in the presence of the electric field, the so-called ponderomotive energy. So if this light is coherent, we can do the mode locking. We can do mode locking, but in the X-ray region, not mode locking in the visible. This was much more difficult. And so there is the first experiment in 1999. We tried to mode lock coherent these high harmonics, the span of high harmonics, a part of them, and we can produce 400 nanosecond. At 1 nanosecond is 10 to minus 18 seconds. So we can produce very, very localized light that open us not only the X-ray abilities to image, but also in time we have a very, very short tool, a delta function, in order to absorb the dynamics in matter. And this attracts a lot of interest, this publication, and this is the news and views presentation in Nature periodical by Paul Corkum. Then we have measured the duration of these pulses using a sophisticated technique that I don't go to go in detail, and we are able really to produce and measure 700 about attosecond using a second order effect of this coherent line to the XUV. Now, is it easy to produce in any lab this kind of tabletop harmonic? This is proved by a project many years ago. This is a station to produce coherent X-rays that the whole length is not more than 1.5 meters, and we are able at this period to produce high harmonics using a gas cell here, and the number of photons are quite enough for in the XUV region, and the spectrum is it's also quite enough in order to go further to use this harmonic to do optics and coherent optics and imaging in this kind of region. Now, another important thing, as I said before, is the coherent summation of light, because we need to have a lot of photons, because the emission of the X-rays is twice per laser cycle, for example, here and here, and we need this point to be coherently summed. And since the laser and the XUV have different index of diffraction inside the material that generated, we need to have the so-called phase matching. So Q is the number of one harmonic, K then is the wave vector of fundamental, minus the K of the harmonic, must be 0 in order to have coherent summation of light in the end, in order to have really very good number of light, because if you want to use a source, you need very good coherent summation of light. Now, let's go back to an experiment that takes place in IPPL in collaboration of the DESI, the so-called accelerator in the NO accelerator in Hamburg in Germany, the Queen's University of Belfast, and ourselves, where we have used sandwich of different gases in order to produce to quasi-phase matching the harmonic. So we have produced harmonic in argon, and in helium we take back there is no any harmonic emission, but in hydrogen, sorry, we can take back the difference in phase between the harmonic generated in the previous argon and the fundamental. So in the next argon slice, we have again coherent summation. In the next slice of hydrogen, we do again we take back the difference between the harmonic and the fundamental, and in argon again coherent summation. And by this way, for example, if we use this kind of 6 slices, the theory say that we will observe an increase of 36 in the number of photons in the harmonic, and this is exactly what we observe in an experimental taking place in IPPL initial part at Pervolia in Rethymnon in femtosecond laser facility. Now, is this harmonic really coherent? We say that is a laser light, but is it coherent? This is a very good experiment many years ago, but we have repeated also in our labs that we can use a filter in order to have only the harmonics and to separate the fundamental for the harmonic. We have the so-called Young experiments where we use 2 pinholes, and finally in the EUV or X-ray camera we observe the Young experiment. We observe the coherent summation of the light here, and we see that there is a perfect spatial coherence, for example in 36 nanometer, where we have really the perfect tool. So nowadays, let's go now from 2015 and up to date. There is a huge increase in laboratories, and especially in states, where they use this harmonic light in order to do really a very good station of coherent imaging in nanoscale. Using different kind of exim. For example, here are the X-rays. We have used a pinhole, a sample here, and this is the diffraction pattern where with sophisticated algorithm, we can go back and see here the sample. This is the plane wave coherent diffraction imaging. Here is the Bragg coherent diffraction imaging where we use a nanocrystal with certain order of diffraction centers in order to put some phase here in the diffraction, and with this way to go back to solve really the Abem transform coherent diffraction pattern in order to observe the material. Here is the ptychographic coherent diffraction imaging where we have an extended sample that we can move by micro positions in X and Y direction. So we can image a longer extended sample with the ability of a few tenths of nanometer. Here is the Fresnel coherent diffraction where we use both a pinhole and extended sample and do the same like before, with using the initial phase that produced by this diaphragm here. Here is the reflection coherent diffraction imaging where we have reflected the light and we have surface patterns and we can do ptychography by the reflection. And there is also a very important is the need of the software that can prepare in order really to go back from the K space to the real space, so we can Fourier transform back with the good algorithm to have all the phases and all the what we need in order to go to come back and have the final output. So let's see now some, it's very now important, for example, to image a virus. Here is the image of herpes virus. You see the diffraction pattern and how we can go back. Here is a big mimic virus where we have the diffraction pattern for harmonics, and this is the 3D structure of the virus. And also I'm sure that in coronavirus there will be also in few months picture of this kind of thing in real coronavirus. So what we do now in XUV in the station in the IPPL, this is the initial design of this kind of image station that we prepare now in our laboratory in Rethymno, where we have here the cell that produce the harmonics. We have here some cells that we do some differential pumping because the harmonics passing through the vacuum. Here is the big cell where we do all the optics of the harmonics, and here is the imaging cell. This is under a certain project of research with EU and Greek funds. So you see here the whole design that is prepared, and you see here really the design how involves and how we produce the different parts here. So you see here the generics cell where here is the gas, and we focus at the exit pinhole of the gas in order to have the harmonics. Here is the big chamber that we do the optics. Here is diffraction gratings that costs a lot of thousands of euros. Here is some sophisticated detectors, and now we are in a stadium in order to put the image in some and try to do the first image of nano materials, of biomaterials, or nanostructured materials. But we have the ability to do not only the image, but also to have pump probe experiment with femtosecond resolutions, where we can have a very big number of images in order to have cinematography of what happened in the micro world. So these are our first, for example, high harmonic. You see the wavelength, and you see how it evolves as we change the pressure inside the gut cell, and you see the phase matching condition. For example, in this harmonic, we have a very high number of photons in this pressure, in 50 torrs of argon at around 30 nanometers. And this is some results that we have a few days ago with the people and the students that work in the project, where we are able to separate the short and the long trajectory. Here is the harmonics, here is the wavelength, and you see that the short harmonic is, the short path of harmonic is located very near with small divergence, while the long trajectory have harmonics that they are extending so much. So you see that in harmonics in the plateau, they have short and long trajectory, while the harmonics inside the cutoff have only intermediate trajectories. So by this way, this is the plasma that inside the gas cell, here is prepared, here is generate the harmonics, and you see some short and long trajectories here. So we are able to separate the short and the long, because the short trajectory have very much have better coherence than the long trajectory in order to use for imaging purposes. So we are ready now. We have already some results. It's published and are very new. We want to repeat it. And now we are exactly in the time to try to do this kind of imaging, X-ray imaging setup. And this is the final schedule, the optical layout, and the final schedule. And we have already some images, but we are in a time now to do the real thing here in our laboratories. Now let me go very fast to the small second part, the coherent X-rays using free electron lasers to do now hard X-rays, not only XUV, hard X-rays, to do also biomedical radiography. As I said before, free electron lasers are very huge and very big facilities. An X-ray free electron laser, for example, here is in Hamburg, is 3 kilometers long. The cost is very, very huge. And also there is a lot of number of photons. There is a short pulse duration. The wavelength is very short. We have magnets where an electron beam comes inside. There is this kind of zingling and produces X-rays at each time of the period here. And this is the free electron laser. And you see here, for example, a femur bone, the biggest bone of humans, and you see the incoherent absorption contrast and the using absorption, the vita function, and you see here if we use the phase difference, using this kind of light, how better is the resolution. I mean, I cannot open this picture very well because I have no space here, but we are ordered to see 3 microns of resolution in this bone using coherent light coming from free electron laser. But it's very expensive, are very few, cannot really involved in the medical system of any country. So I don't want to go in details, but if we have a very high intensity laser and you do the Lorentz force of an electron, you see that some very interesting relativistic phenomena take place. The most important thing is that the electron accelerate together with the laser pulse. So as the laser pulse passes through the material, the leading part of the laser pulse generate plasma, and the laser radiation ants propagate inside the plasma, attract the electrons back of them in very high velocities because of this relativistic effect of the Lorentz force, because the magnetic field is very important. And this is something that we have solved here, and we see that what happened finally after the passing of the laser pulse is the density, the electric field density modulation. So they produce some electrostatic fields, the so-called plasma waves that follow the laser pulse as it propagates inside the material. So what is actually the picture is that we focus a very high, here we need really very high intensity, and we have it more than 10 to 18 watts per square centimeter in a gas material, and as the laser pulse pass through the matter, produces this kind of wave, the so-called plasma waves, where is density difference of the electric field. Here as positive electric field, here is positive electric field. So some electrons that generate by the electric field by ionization can be trapped by this kind of wave and do a surfing in the wave and accelerate it as for example, a surfer do in sea waves and there is a very big acceleration, faster than the phase velocity of the wave. As you see also in the sea, the wave, we have this kind of acceleration. So the electron pulse, the laser pulse pass through the matter. There is a difference, the plasma waves here, where is the difference in density. There are some electrons that trapped in this wave and follow the laser pulse. So by this wave, we have a so-called miniature acceleration. Imagine the previous accelerator that I saw you, the infrared electron laser, are a few kilometers. In CERN, for example, is 27 kilometers. And here we have an acceleration area of only 100 microns. And we can produce, we are easy now to produce many, many MEVs or GeVs of accelerated electrons in this area. You can see here a very sophisticated video. We have also such a kind of video in our department, but so you see the laser pulse passes through the matter. Here is the plasma waves. A satellite traps some electrons here. You see inside the white box. Here is the purple of the electrons, and you see the ziggling of the electron and the acceleration of the electron using these plasma waves. Sorry. So as the electron accelerated, there is a ziggling in this 10 microns area, and every time that there is this change of this term, there is emission of X-rays with an angle that depends on relativistic parameters. And this emission are in hard X-rays. So, typically this theta is only a few millirads. So we have a coherent or semi-coherent X-rays because they produce it in very, very short area of matter. For example, let's see now incoherent X-rays and Rayken experiment where I use the Vita, the absorption. The resolution cannot be less than 1.1 millimeter in the best of the machine that we have today. And see here with coherent X-ray that produces by plasma, by acceleration of particles in plasma, a betatron plasma radiation. You see here, this is a bone that of a woman, and we try to see the, for example, the space that is empty from bone. So we do the osteoporosis, and in this publication they use delta, the phase imaging, and they are able to have a resolution in the order of 10 micrometers, even less, using X-rays produced by this way that I already said to you before, and with about 50 kV energy spectrum and electrons that approach about 0.7 GeV. So see here other example of incoherent X-rays and of coherent X-rays, much more better resolution if we use delta instead of Vita, if we use coherent light produced by laser. See, for example, here the resolution of this is a B, this is a classical X-ray radiography, and this is coherent X-ray radiography using laser secondary sources. The imaging resolution difference is huge. Now let's go in an experiment that took place 2 years ago at Imperial College and Rutherford Laboratory, where Michael Tatarakis and the director of our institute, and also Eugene Clark, senior scientist of our institute, educated, where they use this kind of, they generate the betatron time radiation in a gas cell. Using magnets, they separate the electron beam, and we have here the X-ray beam using a Kapton window. They separate from the fundamental, and they using an X-ray camera. They can do an image of mouse embryo, and you see here the tomography image of a mouse embryo, and you see using this kind of radiation, this is in millimeters, and you see how many details there is. And if you are not impressed from that, see the icon of the X-ray image using secondary laser, betatron laser plasma radiation of this mouse embryo by the group of at the Imperial College, published in PNSA 2 years ago. And now let's go in our institute. We have a very big laser beam, we have a chamber, and we can really do the same thing. And we can have also some sophisticated here experimental setup that we produce electron energy in the order, for example, of 50 megaelectron volt, the relativistic laser beams. We are able to produce up to 250, and this is some typical results. This is the experimental setup. Here is the laser that propagates inside this very big chamber. This is the facility that we can really observe the different kind. So let's see the first results that we have in our institute from beta to radiation. There is much more result, but still unpublished. And you see that we have here, for example, some pin diodes to observe the radiation. And you see here the beta to radiation is localized, while radiation, like, for example, Thomson scattering, that there is in different duration, there is no preferential direction. And this is really the first X-ray, coherent X-ray image in our laboratories that we can use now. We are able to use for imaging purpose, and we have already some very good examples. This is with X-ray camera, and this is one of the images of the X-rays, coherent X-rays that we produce using secondary sources passing through a 10 microns of aluminum filter. So this is the Institute of Plasma Physics and Laser in Hellenic Mediterranean. This is our buildings. This is our big laser with our students and technicians that they work there. And this is the experimental setup. This is the compressor, the vacuum compressor of our big laser system, some other experimental setup. We have also Mike Tatarakis, the director of postgraduate studies in our institute, laser plasma application. This is in English, and we can accept foreigners in this master of plasma, which is oriented also in order to have PhDs after that. So many thanks to my colleagues in IPPL. Sorry for the time, it's a bit more than initially I have prepared. So is the students here, Georgia Andrianaki and Anastasios Grigoriadis, that they work in beta-atom plasma, Steos Petrakis in high harmonic generation. Also, we have some other students that work in theory, like George Koundourakis and Yannis Tazes. We have the master students for Manios Kanolakis working in high harmonic generation, the research engineer and Yannis Orfanos and Alekos Skoulakis that work on high harmonic generation. And this is the senior staff, Dr. Eugene Clark, which is a pioneer in electron acceleration in the past, Vangelos Kaselouris, Kiki Kosma, Dimitris Luludakis, and also the professor team, Yannis Ofitilis, of Vasilis Dimitriou in theory, which is a mathematician with very good knowledge in plasma physics and finite element analysis of different phenomena happening in laser matter interaction. Professor Makis Bakarezos, very well known in nonlinear optics and very good in applied physics, and also our director, Professor Michael Tatarakis, who is the head of the department and pioneer in high power laser matter interaction. I will try to do also a separate special announcement for Professor Manuel Benis, which is one of friend, a very good collaborator, especially in high harmonics and atomic physics from University of Ioannina. And this is the grants that supports our action. And I promise you that in a next talk of our institute in 1 year, we can have very, very good biomedical imaging using this kind of coherent X-rays, either high harmonic generation, either beta-atom radiation. Thank you very much for your passion.
Thank you very much, Nektarios, for this impressive talk. I hope that our guest attendees, they have seen that high quality research can happen in Greece, in Crete, and in our island, within our university, and we are very proud of this. I don't know, I mean, any questions from the audience? I have one question.
Yes, Kostas.
I was very much impressed by this setup that you have done with Belfast, and you use gases in order to generate these periodically poled crystals that we used ourselves in OPOs, in optical parametric oscillators. But you managed to do this by using gases in order to correct the phase loss in each period. So I would like to ask you how accurate you can design this periodically poled gas crystal, let's say, in order to correct this phase this phase distraction. So you correct the phase difference in periodical manner. So using gases, how easy is to achieve this?
This is actually, this is the way how we do that, using certain nano prepared jets, where we have separate gas in each jet. And this is something that is very sophisticated, prepared by 3D printing machines. And now using the tool of 3D printing machine is quite accurate, especially for this purpose. You see here that we have a coherence summation, which is exactly very near the theory. So for this purpose is really very, very accurate in the field of few microns, 10 microns is the difference of the slices here. And this is actually a work that done in DESI laboratory in Hamburg, where we have a very good machine shop, but now this is some years ago. Now 3D printing is everywhere, and I think that this is not really a big task to do this kind of nozzles. And I will give you also one more thing, that we will do exactly the same thing now in beta-tone radiation in the PhD thesis of two of our students to prepare this kind of nodes and to see for the first time how different kind of gases, we have already some results, but how different kind of gases can do really a very good propagation of these plasma waves in order to increase the plasma waves before the breaking, and to produce this kind of coherent summation of the light that generate in different positions.
So, what is the period of this construction down there?
It's something about 10 microns.
Okay, yes. All right. Thank you very much. We have a question from Professor Remediakis from the University of Crete. Yannis, the floor is yours.
Hi, Nektari, thank you very much. That was very inspiring and very, very nice presentation. Impressive work indeed. Quick question from a non-expert. Are there limitations on temperature? I mean, do you really need to heat up the samples during imaging, or can you go to very low temperatures perhaps?
Since everything is light, there is no any limitation. If you have a light that is X-rays penetrate, I mean, I can say that the temperature do, for example, the material liquid or do the material gas. So this is much more easy to penetrate with the X-rays. So I think that increase of the temperature make the plan much more easy. And at the other point is the following thing: since both of the methods that I have shown is very fast, are flashes of X-rays, and the flashes, the duration of the flashes is for high harmonic generation is sub-femtosecond, and for beta-tone is in the order of 1 picosecond. So really there is no any problem if we have very fast acceleration of the atoms because of temperature outside of the interaction region, because we can have very, very good fast flashes in order to observe the whole thing. So we can do many, many flashes in time or in a repeated experiment to do different delays and do PAP-probe experiment in order to have cinematography of the process. Spatio-temporal, very high resolution. So this is the reason why this kind of X-ray source are very, very impressive in order to do the imaging. It's not only spatial, very good coherence, but also in time they have very good abilities.
It is impressive indeed, Nektari, but what about low temperature? Can't you do something that is frozen?
This is a question of mechanics. Since it's light, we need some cold fingers in order to have the low temperature, and we can image everything. There is no any question of temperature. It's because it's light. It's light, and we penetrate the light in. Okay, there is some engineering problems. For example, X-rays and soft X-rays cannot penetrate. Especially soft X-rays cannot penetrate through windows, in order to go inside the cell that we have the very low temperature. But there are solutions. There is way in order to go in a cell where the temperature is very low and image a sample that is kept under very low temperature. I don't think that this is a problem.
I think Yanis is thinking about the vaccine of the Pfizer.
Yeah.
Keep it, in under
Yeah,
in
could be.
minus 75 degrees. But we have a question from Professor Masoud from Iran. So Masoud, the floor is yours to ask the Nectarios.
Thank you very much, Nectarios, for the interesting talk.
Thank you, Masoud.
I would like to ask about the pulses that you used. First, the femtosecond pulses that are used for the generation of the X-rays, and also the properties of the X-ray pulses themselves, and like the duration, the energy, and other things. And what is the limit that is necessary to have to produce such images?
Very good question. Now let's go to the simple thing for the laser. If you want to have high harmonics, XUV coherent high harmonics, the first method, you need a femtosecond laser pulse, less than 100 femtosecond, the less the best, and you need also few millijoules in pulse duration. In IR, and you need IR to be in IR region, titanium sapphire, erbium, or using an opus to go in the IR region. The more the IR, the better. And the number of and the energy that in high harmonics that you produce is in the order of picojoule up to nanojoule, and something about 10 to minus 5, the best of the initial photons of the laser. But since this is in the X-ray regime, you can focus in a smaller area, so someone can reach 10 to 11, 10 to 12 watts per square centimeter using the harmonics. This is something proved because we do nonlinear effects using the high harmonics. Now about the beta tone radiation, you need with laser plasma, you need much more higher intensities. So you need a laser like the one that we have here, a 50 terawatt laser, which is about 1 joule, about 30 femtosecond duration. And the beta tone radiation that we produce in the hard X-rays is in the order of 10 to 7 to 10 to 9 photons. And since the imaging purpose is the diffraction purpose, is not so much, we are not so much interested in the number of photons. If we do, for example, imaging of the diffraction image, if now someone wants to penetrate, so you have a sample that is thick, then you need a higher laser, higher number of photons in the X-rays. And this is the reason why we are working using now different kind of gas cells or different ideas that we have in order to have longer propagation in longer period, in order to have much more number of photons. Now about the characteristics, high harmonics are only 1 to 2 millirads in divergence and pulse duration, which is in the order of 1 femtosecond, either less. In beta tone radiation, the duration is in the order of 1 picosecond, and the divergence of the beam measured in our labs is in the order of 5 to 20, let's say, millirads.
Thank you very much. Just about the femtosecond pulses, as you said, and we know, the longer wavelengths of the pulses that we use, we can go to the shorter X-ray pulses.
If we use the high harmonic generation, yes, and also the same happens also in Betatron, but in Betatron there is no far IR very high intensity lasers.
Mm-hmm. But using the OPA systems, you may have such characteristics in even IR.
using the OPA systems, this is very good for high harmonic generation and XUV. Is not up to now very, very good for beta tone radiation because it's very difficult. There are systems, but it's very difficult to have the intensity you need in order to do the plasma waves. Okay, there is some OPCPA systems now, but which is they do the job. But I mean, in principle, the more in IR you are, the best in this kind of secondary effects, because it's effects that they are in relativistic optics, and according to Keldy's parameter that I guess you know, the more the IR, the better the Keldy's parameter, the more you are much much out of the in the nonlinear regime. You are in tunneling regime, and you are also in relativistic regime.
Yes, of course. What is the wavelength of the system that you use?
It's it's central 810 nanometers. It's a titanium sapphire with 3 amplifiers here, and the 10th in the spectrum is about 60 to 70 nanometers.
Thank you.
Okay, thank you very much.
Thank you, Masoud. Thank you, Nectarios, for the replies. We have a last question, Nectarios, and thank you for your patience from the audience, from our colleague, Professor Kokkinos. How safe for humans are the X-ray emission of coherent laser for biomedical imaging?
This is actually a very good question. I can say it's much more safe than the classical electron tubes that we use in a hospital. The classical electron tubes, even the flashes that they advertise in certain medical centers where they have flash X-rays, the flashes are in the order of microseconds, while here we have a femtosecond or picosecond duration of these flashes. The dose that someone takes depends very much on the intensity that you have. So since the intensity is much more when you have less time duration, we can do the same image with few flashes of femtosecond or picosecond duration, as proved, for example, with the mouse embryo that I saw before, while there is no technology for electron X-ray bubbles, the technology to go less than a microsecond. So the number of photons that you finally, the dose that you finally have, it's much more there. Also, there is another answer to that. If you have a femtosecond or a picosecond pulse duration in your X-ray burst, then there is no really time. The interaction of the matter is with the electrons and not with the nucleus and the protons. Since the DNA, our DNA is in the nucleus, of course, of the biomolecules, there is no any time of interaction with the nucleus. So I think that this is a very good thing, because there is no so much dangers in carcinogenesis using this kind of burst X-rays, because the interaction is only with the electrons. Of course, it's ionization radiation. Of course, there is acceleration of the electrons. Of course, there are this kind of secondary effects, but this happens also in any classical X-ray machine.
For the very detailed replies and the enthusiasm. I think that you are a natural leader, I would say, because you inspire people. I don't know if we have any comments from Giorgos Kavoulakis, if you would like to say something, or we should stop here and continue next week with another exciting talk, I believe. So, Giorgos?
First of all, I would like to say that this is wonderful stuff, Nectarios. I really enjoyed the idea of using the face, to extract information. I did have some things to discuss, but let's leave this between the two of us. I think it's time to. So, thanks a lot. Great presentation, Nectarios.
Thank you very much, Giorgos. Thank you very much, Kostas. Thank you all the participants. I take much more time than I believe before. Sorry for that. Thank you for your patience to stay with us up to about 20 minutes after 12. Thank you very much.
Thank you, Nectarios. Thank you very much.
Thank you very much, Nectarios.
Thank you.
The lecture will be uploaded into our YouTube channel, and hopefully we will see you next week with Professor Valianatos. We are going to change topic. We are going to move more to Earth physics. And then the last talk for December comes from the smart cities from the Professor Kolokocha from the Technical University of Crete. So we would like also to thank our rector that he was with us. And thank you and see you next Friday. Thank you, Nectarios, again. Bye.
Bye-bye.
Thank you, Nectarios.
Bye-bye.